Well, hi everybody, and welcome back to our work on complex numbers. I hope you've had time to think about what happened in the first video and familiarise yourself a little bit with this new concept. Today we're going to go on and start developing an arithmetic of complex numbers. And this is really going to be something that's a bit new to us, so we don't have an idea of how to do any kind of arithmetic with complex numbers, just like we didn't have any kind of idea about how to add and subtract vectors, so we had to develop all those ideas from scratch. So we're going to start off with some simple ideas about complex numbers, and we're going to let Z1 and Z2 be two arbitrary complex numbers, and you'll remember now that a complex number is just a number that has a real part. We're going to call that X or A, doesn't matter what we call it, and then we say plus I times Y or I times B, where this I is the complex number I. So I equals the square root of minus 1. So these are our two arbitrary complex numbers, Z1 and Z2, and we're going to say two complex numbers are equal in the case where the real part of Z1 is equal to the real part of Z2 and the imaginary part of Z1 and the imaginary part of Z2 are also equal. So in the case of our Z1 and Z2, this means that if those two real numbers are equal, then A has to be equal to C and B has to be equal to D. So that's the only case that our two complex numbers are equal. So for example, 3 plus I is not equal to minus 3 plus I. Excuse me. So the y coordinates are the same, so the coefficients of I are the same, but the numbers here, the real part of these two complex numbers are not the same. So those two complex numbers are not equal, and also 3 minus I is not equal to 3 plus I. So the real part of these two complex numbers are the same, but the imaginary part of the two complex numbers are different. So just to repeat, we need to have both the real part and the imaginary part of our complex numbers being the same. So that's about equality of complex numbers. What about addition of complex numbers? So we've got this definition of what it means to add two complex numbers together. So we're starting off again with our complex numbers, arbitrary complex numbers Z1 and Z2. So in this case, I've got A plus IB and Z2 is C plus ID. And we add these two complex numbers together by adding the real parts together and adding the imaginary parts together. So this is the real part of Z1 plus the real part of Z2. So that becomes the real part of our complex sum, and the imaginary part of Z1 plus the imaginary part of Z2 becomes the imaginary part of our new complex number. So let's just go to a blank page so we can do an example of that. So I'm going to start off with my complex number Z1 being 2 plus I, and my second complex number is going to be 5 plus 2I, and according to my rule, I take Z1 plus Z2 by adding the real parts together. So this is 2 plus, oops, I wrote a Z rather than a 2. So this is going to be the real part, so it's 2 plus 5, so that gives me the real part of my new complex number, and then it's going to be plus I times the sum of the imaginary parts of the two complex numbers. So that's going to be 1 plus 2. So altogether I get 7 plus 3I. So that's the sum of my two complex numbers. Now you might notice that I've also got a plus here that sits between the real part and the imaginary part of these complex numbers. That never goes away. We're never going to have a situation where our complex number joins the real part and the imaginary part together in any other sense than the one that we've written down. So this plus that joins together the real part and the imaginary part of the complex number is just a notation to indicate that that's a complex number. So it's not a plus in the way that you might be thinking about it. Okay, so that's pretty easy, adding up adding up complex numbers. What about when we're subtracting complex numbers? Well, this is just a similar definition to the definition for addition. So when we're subtracting two complex numbers, what we do is we subtract the real parts and we subtract the imaginary parts. So let's go back to our example again. So instead here of taking Z1 plus Z2, we might try and take Z1 minus Z2. And the rule says for the real part of this new number, we take the real part of Z1 minus the real part of Z2, plus we have, for the imaginary component, we have the imaginary part of Z1, which is 1, and then we subtract off the imaginary part of Z2, which is 2. So if we put those two things together, this is minus 3 plus I times minus 1. So it's just minus 3 minus I. So when we bring that negative coordinate out the front, we're just subtracting off the imaginary component. Okay, so that's subtraction. So it's very similar to addition. And we can also, when we're not talking about complex multiplication here, we're talking about scalar multiplication. And you'll remember we did that in vectors too. We started off with this idea of a scalar multiplication before we talked about vector multiplication. So what we're talking about here is a scalar, so just some real number k times the complex number z1, and then our z1 is a plus ib. So when we do the scalar multiplication, we just multiply the real part by k and we multiply the imaginary part by k. So go back over here to our example, and our k might be, well, it doesn't matter what our k is, let's say k is equal to 2, and we might want to take k times z1. So that's going to be equal to 2 times 2 plus I, and so we just have 2 times 2 plus 2 times I. So altogether that's 4 plus 2I. So that's our scalar multiplication. So all of those operations, addition, subtraction and multiplication, are pretty straightforward. Now I might just take you over to this slide now, and we're going to see what happens if we represent our complex numbers geometrically in the Argand plane or on an Argand diagram, and we'll see what happens when we add up two complex numbers or subtract two complex numbers or multiply them by a scalar. So when we started looking at sketching points in the Argand plane, what I did was I just drew you a diagram where Z1 might have been here, and I drew it by just putting a point where this was the x coordinate of Z1 and this was the y coordinate of Z1. So Z1 was equal to x plus iy. And we can represent that by a point, but we can also represent it by a line that goes from the origin up to the point Z1. And I'm not going to get it right there, but that's meant to be going up to the point Z1. So what happens then is you can sort of think about this like a vector. So you're thinking about the point Z1 as being here in the plane, but it's also got a distance from the origin. And so when we're thinking about adding up our complex numbers, so here's Z1, and you might think about this being Z1, and that's the point Z1, and here's the complex number Z2, and so the point sits there in the Argand plane, but you can think about it as being represented by that line. And when you add up Z1 and Z2, you can pick up Z1, you could keep the length the same, move it parallel to itself, and you can sort of put it here where I've got this dotted line, and then just like we did with vectors, now that we can represent z1 plus z2 as being that line that ends up at that point. So instead of going z2 plus z1, we're going straight from the origin to z1 plus z2. So that was the same idea that we had from vectors. The same thing happens when we've got z1 minus z2. So here my z1 is the first thing I'm subtracting off z2. So my z2 is here. I can think about picking it up and putting it parallel to itself, except the first thing I've done is I've changed its direction. So I've got the point here, so this was like the tip of the vector going down to the arrowhead of the vector and putting it here. So I've got z1 minus z2. It ends up at that point, or I can go straight from the origin to there. So as you can see, again, it's a bit like what happens with a vector. The other thing that happens like in vectors is with scalar multiplication. So here's my complex number z1, the red part. So it starts at the origin, goes to that point z1, and if I multiply it by a scalar k, then k stretches the thing out here, so I've got the same direction, if you like, as the complex number z1, but I might end up being a longer complex number, or if k is less than 1, it might be short. If k was negative, it would end up going in that direction. So thinking about this in terms of vectors is a good way to think about it if you're drawing complex numbers in the Argand plane. So on this slide, have a go at doing the arithmetic of earlier examples using the Argand plane. So do the addition and scalar multiplication and subtraction geometrically in the plane, and we'll talk about that when we get back into class. Okay, so that's addition and subtraction and scalar multiplication, but of course we want to know how to multiply complex numbers together, so multiplying two complex numbers. And so basically what we do when we're multiplying two complex numbers, and again we're using z1 is just some arbitrary complex number, and so is z2, where a, b, c and d are just real numbers. And we want to multiply these two things together. So I've got the two brackets a plus ib and c plus id, and it sort of looks like a quadratic equation where you had x plus y, 2x plus y, for example, and you wanted to multiply those two terms together, and what you do is you do this cross multiplication. So you multiply x by each bracket and you multiply y by each term in the bracket as well. So let's start off by taking a times c, and then we have a times id, so we'll just write I, ad, and then we've got ib times c, and then we've got ib times id. So if we collect like terms for the imaginary part, and then when we expand out these two brackets, we've got an I in this term and an I in that term, so we've got I squared, and then we've got b times d. So we've got I squared bd, but of course we know that by definition I squared is just equal to minus 1. So this is AC plus I times AD plus BC minus BD. So we've got this is the imaginary part, but these two terms now are both the real part, so we'll collect those terms together as well. Okay, so that's the product of two complex numbers. So you get two parts coming out from a times c, but also this real part coming out when you multiply the two imaginary parts together, because the I squared becomes minus 1. So why don't you have a shot at multiplying a couple of complex numbers together yourself. And again, we'll talk about that when we get back into class. Okay, so that's multiplication of complex numbers. And you'll remember that when we did vectors, we didn't really talk about the idea of division. And that's because there isn't really an idea of division in vectors. In complex numbers, we'd like to have some kind of idea of division, but it's not as simple as it is in real numbers. So before we can start to think about dividing complex numbers, we've got to be able to think about something called a complex conjugate of a complex number. So this is a pretty simple idea. If we've got an arbitrary complex number, z equals a plus ib, it's just any old complex number, then the complex conjugate of z, and we denote that by this z bar, so we just put a bar over the top of the z, is defined to be this number here, z bar equals a minus ib. So basically what a complex conjugate does is it leaves the real part the same, but it changes the sign on the imaginary part. So if you start off with x plus iy, then the z bar is x minus iy. If you start off with x minus iy, then z bar is x plus iy. So it just changes the sign on the imaginary part. So let's do a couple of simple examples. So if this is my complex number, then if I take the conjugate of that, the real part stays the same, but the sign changes on the imaginary part. In the second example, if I take z bar, the real part stays the same, but the sign changes on the imaginary part. What happens if I've just got an imaginary or a purely imaginary complex number? Well, I don't have any real part, so it's, well, I do have a real part. This is really the number 0 plus 3i. So the real part stays the same, and I change the sign on the imaginary part. So of course I can just write that as minus 3i. And if I've just got the complex number 4, then it just stays as 4, because the rule is the real part stays the same and the sign changes on the imaginary part. So I've got, this is really 4 plus 0 times I. So I could write this as 4 minus 0 times I, but really it's just 4. Okay, so that's the complex conjugate. So let's think about what happens now then if we plot some complex numbers in the Argand plane and we take their complex conjugate. So what effect does taking the complex conjugate have on a complex number geometrically? So I'm just going to draw the Argand plane here, and I've got my real axis here and I've got my imaginary axis vertically, and the point Z1 is just 1 in the real, on the real axis, and it's 1 unit on the imaginary axis. So here's my point Z1. My point Z2 is minus 3 on the real axis and minus 2 on the imaginary axis. So it's about there. So that's Z1 and Z2. What happens to my points Z1 and Z2 when I take the complex conjugate? Well, let's think about it. So Z1 is 1 plus I. So Z1 bar is 1 minus I. So the real part stays the same. The imaginary part, the sign changes. So my Z1 bar, the real part stays the same, but the imaginary part changes sign. So I go down here to minus 1. So here's my point Z1 bar. Let's see what happens to Z2. Z2 bar is going to be minus 3 plus 2i. So the real part stays the same, and I change the sign on the imaginary part. So if I go across and I plot Z2, here's minus 3, so that stays the same, but now I've got plus 2i, so I'm up here somewhere. So this is going to be Z2 bar. So the effect that this has geometrically is to reflect the complex number across the real axis. So whatever it was, so the real part stays the same, so the distance along the real axis is the same, but it just reflects it across the real axis, so that if it was a positive imaginary part, it's a negative imaginary part now. If it started off being negative, then the conjugate is is a positive imaginary part. So that's the geometric impact of the conjugate. And this example is another one that I'd like you to try at home, and when we get back into class you can bring this one in if you're having trouble with it, and we'll talk a little bit about it in class. Okay, so what's next? So the next thing we're going to look at is some properties of complex numbers. So when we start doing some algebraic manipulations, these properties of complex conjugates will allow us to simplify some of our calculations. So I'll do the first one now, and the other ones will be things that we can do when we come into class. So I'm starting off with z being some arbitrary complex number, z plus ib, and this first property says that it doesn't matter what complex number we start off with, so it's got non-zero imaginary part, maybe it's got zero imaginary part, it doesn't matter, but whatever the form of the complex number is, if we add that to its complex conjugate, we're always going to get something that's a real number. So it's going to be some number that has zero imaginary part. So that's sort of a curious thing, but it's pretty easily shown. So we're going to start off with z plus z bar, and our z is just going to be any old arbitrary complex number, a plus ib, and we're going to add it to the complex conjugate of a plus ib. So this is a plus ib, and the complex conjugate is going to be a minus ib. So when I add those two things together, I'm going to collect like terms. So I've got a plus a, so that's going to be my real part, and ib plus minus ib, so it's going to be ib minus ib, and you can see here that that term is going to be 0, and I'm going to be left with 2a. So you can see it didn't matter what my a and b were to start off with, I'm always going to end up, whatever the sign of this was, and this could have been a minus ib, the complex conjugate is going to keep the b part the same, but it's changing the sign. So when I add these two things together, this term and that term are going to cancel out. Okay, so let me just go to the next page then. And this has got plenty of space for you to try those other properties at home, and we'll talk a bit more about those when we come into class.